Okay, welcome back everyone. So today we're going to be making another video, except this is going to be a bit different because I'm going to try something new. Basically, I'm going to be making a video where we just, solve a Putnam problem. So here's the Putnam problem. It's pretty basic. So the polynomial p of x has integral coefficients. The leading coefficient, the constant term, and p of 1 are all odd. Show that p of x has no rational roots. So let's write up that question here. So we have integral coefficients just mean integer coefficients, okay? Leading coefficient, okay. So polynomial p of x has integral. Let me see if I can actually lower the font size because that's kind of high. So let me just make it a bit better. So p of x, okay. P of x has integral I'll just abbreviate it as coefs. Okay, and we have the leading coefficient, the constant term, and p of 1 are all odd. Okay, show that p of x has no rational roots. So we have constant c term is odd, p of 1 is odd, and the leading coefficient and leading coef is odd. Okay. So now we want to prove that this has no integral solution, no rational solutions. So I think the method that we can employ here is basically proof by contradiction. Okay, so let's see. Let's make some observations before we do that. So p of x has integral coefficients. Leading coefficient, constant term, and the p of 1 are all odd. So that p of x has no rational solutions. Okay. So notice that p of 1 is just the sum of all the coefficients, coefs. Okay, so p of 1 is nothing but the sum of all the coefficients. So that means that it is actually odd. Well, no, sorry. The question told us that it was odd. So we know that the sum of all the coefficients is odd. And from this, I'll just write just our first observation, and second observation, from 1. Okay, so from 1, let's see. So we have from 1. So if the sum of is all odd, and we know that the last term is odd, then we know that the total number of odd coefficients, total number, or let's just write it like this. There is an odd of odd coefficients. coefficients. Okay. And that's because, well, we know that our last term is odd, and we know that if we add an even number of odd terms, we get an even term, because then we can just factor out a 2. So we don't want. So that's not the case here, since P1 is odd. So it must be an odd. So that means there must be an odd number of odd numbers, right? And that's what we found here. Okay, so what can we do now? Okay. So I think we can employ a strategy, like I said. So, observation. Okay. Strategy. We can show that we can do a proof by contradiction. So we can test, we can disprove, doesn't matter which order, so disprove evens, odds, and then rationals, or I'll just write fractions. Okay. Disprove. So it doesn't matter which order we do it in. I'm just gonna go from evens to odds to fractions. Seems like a good way to go. Okay, so let's start out with. So here's a claim, or statement. So statement. Let's see. Well, I'm not gonna write the statement yet. So. Test. Let's just test evens, and we note it, and we have to note it. So I'm probably doing this out of context here. So we're looking to see if we plug in evens, odds, or fractions, we want to show that none of those will work. If we plug that into our polynomial p of x, then we will never get a root. And we're doing this. We're proving this by contradiction. Test evens. So we'll call evens to be, let's say 2n, or let's say 2n. So we can just do p of 2n. This is always going to be an even number. Is just equal to. Well, let's see. So we'll have something here times 2n to the n, okay, plus something here times 2n to the n minus 1 all the way to plus something times 2n, and then plus some constant here, which is odd, and that's key. Okay, so let's see what we can do here. So we know that, well, let's see. So we know that the sum of all the coefficients is odd. Okay, so the sum of all the coefficients is odd, and there's an odd number of odd coefficients. Let's see. So what can we do with this? Well, we know that basically an even number, if you multiply it by an odd number, you get an even number back. And let's see. Okay. So here's the key thing. So let's just take a look at this section here. I just realized something. So if we take a look at this section here, then notice that we can either have odd, or since these are integral coefficients, we won't have fractional coefficients. So there's either an even or an odd number here. Okay? So So we know that an odd number, so odd, okay, odd times odd odd times even. An odd number times an even number is just an even number. And we also know that even times even is obviously just an even number. So as a result, we can conclude that this this entire area, no matter what we put in here, is always going to be even. And we know that this last term is odd, so an even number plus an odd number is always odd. So this part is even. This is some odd number. And then we know that odd. So how should I put this? Where should I put this for that matter? So we have even plus odd equals, even, odd. Okay, so there we go. So we've just shown this is a contradiction here because 0 is not odd, right? So essentially we've shown that this can't be equal to 0. So that as a result, no even number is a root of this polynomial. Now let's try testing out. Okay, so we'll just make this claim clear. So even numbers are not roots of p of x. Okay, so now let's go into the odd numbers. Test odds. Okay, so we'll just call the odd numbers odd. Okay, we'll call them m. Odd number, okay, m. So just have p of m. I think is there a select tool? I try just getting rid of this. Oh, that's helpful, yeah, so we need more space for this. Okay, great. So let's try this out. So p of m equals some number times m to the n, of course, plus something times m to the n minus 1 all the way to plus something times m, and then plus some odd number. Okay. And it's important to note that, so here's something we can notice. So we notice that this is either even or odd, and we notice that some even. Okay, so something times some. Okay, so we notice something times some odd number to the n. Okay, well, let's backtrack here. So we've tested evens, okay? And let's see what we could do here. Let's take a better look at this and just take our time here. Okay. So odds. So let's see. So from one there's an odd, so we know that there's an odd number of odd coefficients. Okay? So an odd number of odd coefficients. And let's see. So let's focus on the parity of it, or just like the oddness or the evenness of this. So we can notice that, well, let's see. So notice that an even number times m to the whatever power, to the whatever, is always going to be odd. Okay? Even numbers don't change the parity. So we can ignore all the even coefficients. So we're left with an odd number of odd coefficients. So as a result, so we know that, okay, I should probably backtrack here. But if we have an even coefficient here, we're still going to get an odd number. Okay? So evens don't change the parity. But since we have an odd number of odd coefficients, then okay, let's see. So let's check this out. Okay. So the key here is the parity. So here we have an odd number, and let's try focusing on this, kind of like last time. So let's try to make some connection here. So if we have an even coefficient, we'll get an odd number. No matter what power here, we'll get an odd number. So let's see. Okay. Let's check it out. So let's make another claim here. So we can say that this is P of n is just congruent to everything, okay, except everything except so just the same thing except excluding the odds, excluding the even coefficients, coefs. Okay. And okay. And everything excluding the even coefficients. So as a result, we'll just get an odd number here. Okay? So mod 2. Okay, and that's why we use the congruent sign here. And basically this just means that they have the same parity. So as a result, we just get that this is an odd number. Or, hold on. You see, this is the key, because we have an odd number. If we have an odd number of odd coefficients, then we're excluding the even coefficients. So if we have an odd number of odd coefficients, we know that we won't have an even number of even coefficients. So as a result, we'll just get that an odd number. So this will be an odd number. Odd, right? An odd number. And this is an odd number. Except the thing is that we know odd. Okay, so let's backtrack here. So this is Okay, so we know that there's an odd number of odd numbers, so we can't have an even number of even numbers. I know I'm repeating here, but it's key. So as a result, we'll just get an odd number since there's since there's an odd number of odd numbers. So we know that this is a contradiction, right? Because 0 is an odd number. So let's take that. So odds can't be roots. Okay, I'm going to duplicate this tab. And then I'm just going to select everything. Okay. And then I'm going to delete so that we have a clear one here. So pen. So now we want to test fractions. And we'll take the fractions to be, well, let's just say m over n. Okay? So let's consider p of m over n. This is just going to be, we'll give it coefficients now. So we'll give it like a1, let's say, okay, a1 m over n to the n. Oh, yeah, I probably shouldn't use n there, because to the k, I'll just use to the k. Oh no, I'll just use k on the bottom then. So I'm gonna delete that. Now we're gonna have k here. Delete that. Okay. K. Plus a2. So this is to the n. M k to the n minus 1 all the way to plus a, okay, plus, yeah, technically it's plus an, yeah, so plus an times, plus an minus 1, yeah, times mk plus, yeah, maybe I should have gone with this. Okay, that doesn't really matter. Okay, plus a n. Okay, so this is just an odd number. Sorry about that. That might have been loud, I'm not sure. So hope that wasn't too loud. Okay, so test fractions, okay? So let's try to look at this. And we're going to do this by contradiction. So we're going to assume that this is equal to 0. So this is equal to 0. 0 equals a1 m to the n to the... Okay, and I would also want to say that m over n is in its simplest form. Simplest form. So m over k. I'm not going to rewrite all of this, so... Okay, I'm just gonna... How should I do this? Okay, simplest form. Okay, so notice that, so this is just... Gonna get rid of this. So notice that this is just equal to 0. So this equals 0. Okay? So notice that we know that m and k cannot both be 0. And that's because, well, sorry, they cannot both be even. Because if it's in its simplest form, right, if it's in its simplest form, then, well, if they were even, then you could make them even more. Well, then you could factor out a 2 and then simplify them further. So, as a result, they cannot both be even. So, m, k cannot both be even. Okay. Okay, and actually what I'm gonna do is I'm gonna actually get rid of the denominator. So that's just gonna leave us with so 0. So get rid of denominator. So 0. So basically just multiply by k to the n. So for the first term, we just have, let's see, so we just have a1 m to the n, right, plus a2 m to the plus a2 k m to the n minus 1, right, all the way to plus a n minus 1 k, let's see, so basically k to the n minus 1, okay, and then we just have m. Okay, I'm pretty sure that's correct. Just making sure. Hold on. That might not be correct there. So if we multiply by k to the n, it should be correct. Yeah. Let me just double check the last few. K to the n minus k to the n. Yeah, okay, it's correct. Yeah. Pretty sure. Okay. And then plus a n, and then just k to the n. Okay, that's pretty key. So, there we go. So we've cleared the denominator. So now, there's basically two cases here. So we've gotten rid of the, well, we have a few cases. So let's split this up into cases. We have shown that m and k cannot both be even. So cases. We have, let's see, let's check this out. Okay. I'm just making sure that I'm doing this right. So those are coefficients. Okay. Yeah, so m and k cannot both be even. And then let's check to see if m is odd, k is even, and then m, k both odd, and then k odd, m even. So those are our cases. So let's try case 2. So this is our case that we're going for. Case 2, or sorry, we'll just try m, k, r, odd. So let's see what happens if they're both odd. Well, if they're both odd, we see that this term, so if this is odd, this term will be odd, of course. And if this is, so we get an odd multiplied by an odd. Okay. So we know that there's an odd number of odd terms that always seems to come into play. Okay. So let's see. So if m and k are both odd, and we have an odd number of odd coefficients, so we know that m to the n, k, so we know that 10, so this is our 10. We know that m to the something times k to the something. So if these are both odd, this will always be odd. We know that. Okay. Oh, whoops. What else can we see? So let's see. Okay. Well, let's see. So if we have an even coefficient here, we're still gonna, so we know that if we have an even coefficient, if we multiply an even coefficient by an odd number, so an even coefficient to any power, in this case, will be multiplied by an odd number, will give us an even number. Okay. So the odd number of odd numbers, odd coefficients. Okay. So it looks like we will get some even numbers here. So let's see. So odd. But we still notice that if we, okay. So I think my take on this will be that all the terms, since they're an odd number of odd coefficients, so if for all the odd number coefficients, that will always be an odd number in this case. But if we have an even number coefficient, that will always be an even number. But we know that an odd number plus an even number is just an odd number. So we know that this is not true. So, well, we know that 0 is not an odd number, so this is another contradiction. Okay, so contradiction. 0 is not odd. Yeah, okay. That makes sense. Hopefully you could conceptualize that, because I'm not sure how I would write that down. So case. Okay, so next case. So let's just take, let's say m is odd, k is even. Okay, so what happens then? Okay, well, m to any power will always be odd. That's for sure. Okay? and k will always be even. Okay? So I feel like this is a similar strategy here. So here, I'll just try this. I feel like this might work better. So let's take n to be even first and k to be odd. Okay. So let's see here. So if m is even, here, let's make a claim here. So m is even, an even number to any power, and so some odd, okay, some odd times even to n some, okay, well, actually, some number times even to the whatever power. So some number here is always going to be, the parity of this is always even. Okay. So we're taking m to be even. So all the terms that have m will be even, of course. Right? Let's see. Okay, and yeah. Okay, I'm just trying to reason through this. So if that's the case, so okay. Okay. Okay, so I feel like for all of these cases, it's key to know that any number, so an odd, adding an even number to anything will make the parity, will not change the parity of that value. So if m is even, then we'll get an even value for all of these m's. But we don't have an m value for this last term here, so that doesn't have an m value. Interesting. Okay. But we still know that, let's see. Wait, that's peculiar. Oh, plus an. Okay. So we know that this is odd. So, and kn is odd, so this term is odd. So the constant term is odd. And well, let's see. We have an odd number of odd coefficients. So I feel like we can make the same assumption here. Hold on. So let's check it out. So odd number of odd coefficients. M here. Okay. So even if we have no m here, we're still gonna get, so adding even to an odd number, so this is still odd here actually. And this would be our only section. So this is all odd. Okay? That entire thing is odd because it contains m. Oh, sorry. Oh, I'm thinking. So this is odd. And this whole thing is even. Okay, so here we go. So this, for some reason I was confusing myself. So this whole thing is even, but this is odd. So because these contain powers of m, and anything that contains powers of m, of n, or any value will always be even. Okay? So because that makes sense. And even doesn't change the parity. So even plus odd is always going to give us an odd. And here's another contradiction. So, contradiction. Contradiction. And finally, for our last one here, so we have, okay, and this is similar. Okay, so M is odd, K is even, and this is similar relationship. So notice that there are an odd number of odd terms. Okay, hold on. So K is even. Okay. So we have that this term. Oh wait, did I write that up incorrectly? No, I wrote that up right. Okay, yeah. So this term. Okay, well, never mind. Oops. So there are. Okay, so similar to this, except we have an odd number in the power here. So K. Okay, so M is odd, and K is, so K to any power is just still going to be odd. Or sorry, yeah, K to any power is still going to be even. M is odd. So here, since we have an odd number of odd terms here, well, we have an odd number of odd terms. Okay? So here we'll just write similar to last case contradiction. So this is also a contradiction. So there's our proof. So this is the end. So I hope you enjoyed this problem, and have a nice day.